And we are back. This is the Diabolic vTutor, and today we're going to be covering graphing polynomials. So we'll basically be incorporating things like end behaviors, intercepts, and then factorizing polynomials for the explicit purpose of graphing. So let us begin. Oh, I don't even have my drawing program. Whoops. Hold up. Where did it go? Alright, there we go. Okay. There's just a few things to go over. Thankfully, this isn't exactly a super difficult topic, at least in my opinion. It's just graphing. We need to understand some basic concepts first, and among them, we're going to be talking about end behaviors, but going back just a few steps, what exactly are we graphing? We're graphing polynomials. So we've been working with that for quite a bit. So the nice thing is that our factoring skills will come back into play. So you'll be given some sort of generic polynomial, and then you will have to factorize it. It is almost always factorizable when you're doing these type of problems, unless someone's deliberately trying to troll you. But for the most part, the polynomials you'll be given should be factorizable, so you'll be using whatever factoring algorithms you will have. Primarily synthetic division, probably. But then you might have to deal with specialized factoring methods as well. But again, for the most part, it's just going to be fairly straightforward in terms of the types of problems you'll be working on. So polynomials. When we talk about polynomials, there are generally two major types. You may see many different types of funky-looking graphs. Something like this, for example. Or you might be seeing something like this. Or even something basic like this. But they all have things in common with each other. So the first concept we need to go over is end behaviors. Basically, what are the long-term trends in your graphs? So let's start with the easiest function to talk about. It's going to be the linear function y is equal to x. So linear function, this is degree x power to exponent 1. So when you decide to graph this thing, what do we have? We have our x-axis, and then we have our y-axis, and then you're going to have your line. Let's color this red. It's going to be piercing through the origin, like so. This is just very basic stuff. Slope of 1, so forwards 1, or rise of 1, run of 1. Yes. I can't speak today, apparently. Or rise of 3, run of 3, for example. So there's a constant rate of change, but pay attention to the so-called end behaviors. And when I say end behaviors, those are simply the long-term trends in how your function behaves when your x values are super, super large. So visually, I'm referring to these arrows. The bottom arrow and then the top arrow right there. Quote-unquote top, quote-unquote bottom arrows. So what exactly is happening with this particular arrow on the right-hand side? All this is saying is when you have larger x values, your y values are also larger. Case in point, we're going to do a very simple table. So if your x value is here and then your y value is there, we can see the trends in the number behaviors. So if your x value is 1, then your y value is 1. So that's not a big deal. If your x value is 10, and then your y value is also 10. And if your x value is 1000, then your y value is 1000. So you can see this, as the x value increases, so does the y value. So if your x is 10 to the power of 10, for example, then your y value is also large, 10 to the power of 10. So as your x values are ever increasing, so are your y values. And this arrow encapsulates that very idea. The fact that the arrow goes kind of a diagonal upwards So if you were to break down this arrow in terms of vectors, there's a rightward movement, and then there is an upwards movement. So there's an overall trend of going up. So when x value increases, then the y value also increases. So that is the end behavior on the quote-unquote right-hand side as the arrow goes upwards. Again, moving to the right and then moving upwards. And then you draw this little diagonal visual. And then the kind of the similar situation happening in terms of this particular arrow. So what's happening right there? It's basically the same trend, except now you have negative values. So let's draw up the table yet again. So if your x values are here and then your y values are there. If you have x is -1, then y is -1. If your x value is -100, then your y value is -100 for this function as well. If your x value is -100,000, then your y value is also -100,000. And then of course, if you have -10 to the power of 10 to the power of 10, then your y value is also -10 to the power of 10 to the power of 10. So what does this mean yet again? As your x values are decreasing, your y values are also decreasing. So again, when we're moving to the left-hand side of the x-axis, that means we're picking smaller x values. And then when you travel down vertically on the graph, that means your y values are decreasing as well. So again, as x values decrease, your y values also decrease. So these two vectorials, if you combine them in your head, that's going kind of diagonal downwards. And that accounts for this particular arrow end behavior right there. So we can summarize this using some new grammar if you haven't learned this yet. So as the x value, let me write it. As x increases, so this just simply means as x gets to a larger and larger sized positive, then y also increases for this function. You could also say it using a different arrow notation. So as x approaches positive infinity, comma, y also approaches positive infinity. So this is the same way as saying this, and then this is just a more grammatical way, written way of saying that. They're synonymous. So that is for the right-hand trend. I'm going to colorize that just a little bit. So let's colorize as orange. This one's going to be the grammar phrasing for orange. And then, of course, you have magenta. We need to have our own phrase for that one. So as x value decreases, then the y value also decreases. So a synonymous way of saying this is simply going to be as x approaches negative infinity, and y approaches also negative infinity. Nice. So that, again, that's summarizing this particular portion right there. And just a few things to make note of. Infinity is not something called a discrete value. Infinity is not like 5 or pi. It's not an actual number. It's just an idea that there's the numbers can what's the word? There's no end to the numbers. There's no definite value that you are quote unquote stopping at. So when we say x approaches infinity, we're just saying as x gets increasingly larger in the size, or if x approaches negative infinity, then x is increasingly smaller and smaller. So that's point number one I want to point out. Infinity is not a number. So back in the days when you're like in maybe elementary school, and then you remember how kids go, they're like, I'm greater than infinity plus 1, but you know, that's when you learn more and when you get a better idea, when you have a better grasp of what infinity is, that statement is kind of whack. Although it's kind of interesting because you do have different sized infinities, but we're not going to talk about that because we're focused on just determining end behaviors of our polynomials. And again, just to recap, this is a linear function. it's fairly straightforward. When your arrow, your linear function either goes quote unquote up or goes quote unquote downwards. And we're reading from left to right, following standard Western style reading from left to right. That's why this line is tilted upwards. Okay, and then I think there's one more other thing I wanted to mention, and it was, what was it? I already said that infinity is not a number. It's not something called a discrete value. And then the other thing was, oh, yes, the distinguishment in a little bit of terminology. It's kind of confusing because, I don't know, there's an idea that a number is smaller, and then there's an idea that a number is smaller in size, and then there's an idea that a number is large, or there is a number that is small but large in size. So let me just distinguish between those two real quick, because it does kind of cause some funky misunderstandings when we're talking about stuff like this. So when we have something like negative 1,000, for example, or 1 million, let's say, this is a small number in comparison to something like 0. So 0 is nothing, but this one is negative 1 million. So it might feel like it's something, but we'll get back to that. But negative 1 million is smaller than 0. So just by strictly using the word smaller or larger, negative 1 million is smaller than 0. And then if you have 10, 10 is larger than 0. So therefore 10 is larger than negative 1 million. So that's it for larger versus smaller only. And then of course you have something called size, magnitude. So 0 has a distance from 0 of 0. So 0 isn't any spaces away from itself. So 0 has a magnitude of 0, which, if you recall absolute values, that's the idea of what we're talking about right now. So 0 has a magnitude of 0. 10 has a magnitude of 10 because it is the size of it, the distance of it from 0 is going to be 10 spaces away from 0. But when you get to negative 1 million, negative 1 million is a million spaces away from 0 on the x-axis. So therefore, negative 1 million has a larger magnitude than does 10, and subsequently 0. So negative 1 million has a larger size than 10 and 0. That's called magnitude. But negative 1 million is smaller than 10. Isn't that fun? Don't we just love this style of a vocabulary? If only we had a different word choice. But so to circumvent the confusion, just simply use magnitude when you're talking about the bulk or the size of a number from 0. And then use smaller or larger when you're referring strictly to positive numbers or negative numbers. Negative numbers are always smaller than positive numbers. But negative numbers could have a larger magnitude than positive numbers. So, fun times. Alright, so that's just strictly end behaviors for our linear functions. But what if we get to more interesting functions like parabolas? So we have y is equal to x squared. We've talked about parabolas extensively. What are we doing for that one? If you remember how to graph this, I hope you do. So this one is going to be, let me plant it as red. So for this particular function, it has a vertex of 0, 0, if you recall. You're always entitled to put a 0. So this is called the vertex form in review. You have this number here and you have this number there. You can use it to generate your vertex, which, this is unnecessary, but it's nice to think about it. So there's the vertex planted at 0, 0. And then if you recall, the movement is 1 to 1 to get to your next standard point, and then 2 to 4 to get to that next standard point, and then 3 to 9 to get to your third point, and then you just connect them as smoothly and artfully as possible. This is probably off to the side too much. It's more like, well, more like that. Okay, there you go. I gotta beautify that. And if you recall, you can also use the line of the axis of symmetry to exploit the graphing and make it easier for yourself. So this point is one space away from the central axis of symmetry, so this corresponding point is going to be on this side. And then this has a certain distance d1, and then therefore there's a distance d2 to reach the point that's been reflected. There it is. And the same is true for this, and if we call this d3, then this is d4, and d4 is equal to d3. Alright, and that's basically how the graph looks. Let's describe this in terms of end behavior. You can see that both arrows are going upwards. So that's indicative of something. So let's talk about the patterns. So for this particular one, you have going forwards to the right and then upwards. So that is going to be as x increases, y also increases. And that should make sense. Because if you put in a value for x here, it's going to get squared. It's going to become positive, if it's not 0. And then this y value is going to get very large. So if you plug in something like, let's do a table real quick. If we're talking about the xy table yet again, this is for a quadratic now. If you plug in 1, then you get 1. If you plug in 100, then you get 4 zeros on the back, which is 10,000. If you plug in something like that, then you have a lot more zeros, right? You have 8 zeros. So 1, 2, 3, 4, 1, 2, 3, 4. Okay, so you're going to get absurdly large values. So as the x values are increasing, your y values are getting increasingly large as well, which we are summarizing using this grammar. Or again, you can just simply use the as x approaches a larger number, then y values also approach a large positive number. All right, let me see. Someone just texted me. Okay. Just Rumi asking about dinner plans. I have no dinner plans. Alright, so that is the right-hand side end behavior description. That's describing this one, and then we can describe the left-hand behavior as well. So remember what this one is doing as we are going towards the left-hand side. What's happening in terms of our number trending for that scenario. So if we do the table of values, let's say x is equal to -1, then y is equal to 2. Because there's a squaring, it becomes +1. And then if x approaches -100, for example, then y approaches +10,000. So what's happening? Well, let's do one more just for a good measure. So if x approaches 100,000, and then y approaches positive. How many zeros is that? That's 5. So I need 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. But just to illustrate the point, so as the x values are getting larger, negative in size, magnitude, then the y value is getting larger, positive, also in size, which accounts for this upwards trend on the left-hand side. So this is just a way, this is just the data, but if we were to express it in terms of this type of notation, as x approaches negative infinity, then y approaches positive infinity. Because again, if x is a large-sized negative value, then the y ends up being a large-sized positive value. You could observe the trending pattern like so. So that's why we're moving upwards like that. I should do this in magenta. Whoops. Again, as x approaches negative infinity, the y value approaches positive infinity. And that describes the end behaviors of the left-hand side and then of the right-hand side. So, not too bad. At least, I don't think it's too bad. So, what if we get to something that's that's neither linear nor quadratic, something with a higher degree? The next one up is just cubics. So you have y is equal to x cubed. So that one's if you have 0, 0 cubed is 0. If you have 1 cubed, it's going to be 1. If you have negative 1 cubed, it's negative 1. If you have 2 cubed, it's 8. If you have negative 2 cubed, it's negative 8. Just connect the dots as smoothly as possible. There is a pattern very similar to the cubic with a squaring, similar to the quadratic, the squaring situation. So see if you can describe these end behaviors for this cubic function. Well, this one is going upwards. Remember, this arrow is kind of tilted ultimately, so visually it's hard to represent, but the idea is this arrow is slightly tilted. It's like kind of like this in your mind's eye, just picture it as being slightly tilted. So as the x values are increasing, the y values are also increasing. Yep. We can describe this as x approaches positive infinity, then the y value approaches also positive infinity. And then that, again, this should make sense. Because if you do a table of value for this one, if you put increasingly larger sized positive numbers for x, then the y values get progressively larger in size and positive as well. So check it out real quick. I don't like working with cubics because the numbers start to explode a lot. So if 1 cubed is 1, 10 cubed is 1,000, and then that 1 cubed is, I don't know how to pronounce it off the top of my head, a billion? This is a million, this is yeah, this is going to be a billion. You can see the explosive growth of the numbers. So as x values increase, then the y values also increase, which is encapsulated with this particular statement, and that's describing the right hand end behavior. We can do the same thing for the left hand. You notice that it's quote unquote going downwards. As downwards is negative y values. Rumi's asking if I'm craving something. I'll just say I'll trust his judgment. Okay. So again, describing this particular end behavior, as you notice the arrow is quote unquote going downwards. We can summarize that. We are moving to the left hand side. So as the x values approach larger sized negative values, magnitude negative, and then the y values approach also large sized negatives. So that's end behavior description of this one in sort of a verbal statement. my roomie just said McDonald's. That's trash. Let me text that real quick. Trash. McDonald's. Alright. That's the end behavior of the left-hand side, and then that's it. Not too bad. Now we can have some generalized situations, and remember this is applicable only to polynomials, at least for now. When we get to different functions, then it's going to have similar ideas, but these rules I'm about to explicitly spell out are strictly for polynomials. So if you have a polynomial, and that polynomial is of an odd degree, so let's say odd up here. It's of an odd degree, then it's going to follow the linear function style of going down, up, or up, down. So this is what I mean by down, up. So one side is going to be pointing downwards, and then the other one will be pointing in the opposite direction. And that's going to be the end behavior situations for odd-powered polynomial functions. So for example, if you have x to the power of 1, that's a linear function. It's going to go like this, as we already talked about. If you have cubic function, x to the power of 3, then it's going to be doing something very similar, except it has the little twists and turns like that. So what if we have something like y to the power of x power 51? This is an odd-powered exponent. This is just x. It's going to follow this typical behavior. First, you have this downwards trend, and then you have this upwards trend, and it's going to look something like this. As you see, it has the core tenet of a linear function. because odd exponents don't get rid of negative values. So if you raise something to the power of positive 51, let me say it again. If you raise a negative thing to power 51, the negative is not eradicated. If you raise a positive thing to exponent 51, then it will be still positive. So that's why we have this downwards, upwards trend from left to right. So again, if you have y powered, if you have y is equal to x, and then x is to an odd power, and is an odd integer. Let's do integers for now, because if you have fractional exponent, that leads to other shenanigans. So we're strictly talking about integers. So if n is an odd integer, then you have the typical linear function n behaviors. How do I spell behavior? Behavior. This ain't British, so we're going to put it like that. Okay. Alright, so n behavior meaning we have a down uptrend or an up down trend. So either like this or it's either like that. Because again, the negatives are important because if n is an odd degree, then the negatives are not gotten rid of. Versus, in contrast, if n is an even integer, then you have the parabolic-like behavior. So the n behavior will be either up, up, or down, down. So let me illustrate that real quick. So you can have upwards, upwards, like a parabola. Because again, if you have something like x to the power of 2, and that's your function, if you input negative values, those negative values will get raised to an even exponent, and then even exponents will eradicate the negative sign, so things end up being positive. That's describing the n behavior. It goes up, up. Or if you have a negative coefficient in the front, let's say you have y is equal to negative 3x squared, for example. This is going to be a quadratic situation, but because of the negative a value in the front, it goes downwards, downwards, because if you square a number, it will always be positive or 0, and then if you apply a negative to it, everything becomes negative or 0. So hence this downwards situation. So either that or that. And that's basically it for the n behavior rules. We'll talk about, I guess it'll make more sense when you actually apply it to situations. So n behavior, we are finished with that. Let us talk something about, no, let me show a few examples because I think it'll be a lot clearer. And I'll also make note of a few other things. So if you have y is equal to x to the power of 31, for example. Oh, wait, I should backtrack just a little bit. I'm backtracking just a little bit. Is an odd integer. I shouldn't say integer, because if you have something like x to the power of negative 5, that is an integer, but it's a negative value, which is a reciprocal situation, which I shouldn't mention at this point. That's going to be for a future lesson, so let me erase this thing right here. So not integers, just whole numbers for now. Yeah, it's an odd whole number. I'll use the pound sign. It's not hash mark, it's a pound sign. To all those older folks out there. And it's an even whole number. Pound sign number. Not hashtag. Yeah. So make sure it's a whole number for whole numbers. No negative values. Okay. Just a disclaimer. So we have y to the power of x. I keep saying it the wrong way. Y equals x to the power of 11. What's the overall end behavior for the situation? What will it look like? Well, it's going to be an odd, so we know, and then there's a positive invisible 1 in the front, so it's going to be doing something like this. Following again, like a linear function. if you have exponent 1, it's going to go like this. Fairly straightforward. You have the matching end behaviors. As x increases, y value also increases. And you have the negative behavior. As x decreases, then y value also decreases. But what if you have more than one term, right? What if you have like y is equal to x to the power of 31, and then you have something like plus x to the power of 2. And then we'll put like 1000 right here. Alright, so if you're given something like this, what is the end behavior for this one? And you might be thinking, well, which rule am I going to apply? This is x power 31, so that's odd, and then this is x power 2, that's even. This is technically x power 0, which is also even. So what gives? Which rule do I apply for this one? What are the end behaviors for in this situation? And the end behavior is strictly on x to the power of 31. So it's going to be overall downwards trend, upwards trend, like this. Because again, this is odd powered, it's going to do a linear like behavior in terms of end behavior. So as x increases, as x approaches positive infinity, then y also approaches positive infinity. As x approaches negative infinity, then y value also approaches negative infinity. But why is that? And it's getting a feel of the numbers. This is something called end behavior trends. If you think about it, this is x to an absurd 31 exponent. This is only x to the power of 2. So which one, quote unquote, grows faster? So if you plug in a number into this x and you plug in the same number into that x, you will see the differences in how quickly those numbers will grow. So let's check that out real quick. So for example, if you plug in a 1 and then you raise it to the power of 31, it's going to be the same as 1 to the power of 2, right? But if you have 10 to the power of 31, that's a whopping 31 zeros. But if you raise 10 to the power of 2, that's only 2 zeros, right? Think about that. So going from this number crunching to this one, that's a huge jump. And going from here to here is a relatively small jump. So what that means is the x to the power of 31 will overtake the x to the power of 2 in the long term. That's why we're talking about long-term end behavior, because that's when you have exceedingly large x values and they're only getting larger and larger. So again, if you're raising a large value to 31, it's going to be a much larger size number than raising the same number to the power of 2. And by extrapolation, this is just a constant. Constances don't grow. They don't change over time depending on your x. So this one is stuck forever at 1000, whereas those two terms can easily outgrow 1000. So even if I had made this as 1000 to the power of 1000 to the power of 1000, that's an absurdly huge number, but it is fixed. It's static. It will never change. It's a constant. So definition of constant means unchanging. So it will never deviate, grow larger than this number. But x to the power of 31, there is a number that you will cross at some point. And if you raise it to the power of 31, it will exceed this thing right there. I hope that makes sense. So again, when determining the end behavior, you go off of the one with the highest degree and you follow the sign in the front. Because again, the one with the largest degree, the term with the largest degree will outgrow anything else with smaller degrees, especially things that don't even change, like constances. Alright, so again, for this particular situation, you're going to have this downwards, upwards behavior. It might look something goofy like this. I don't know. I didn't do the math for this one, so I'm just being very artsy about it, but you can imagine it being something like this. How many loops? Don't worry about that at the moment. Just understand the end behaviors for this one. Alright, so going forwards, if we have something similar to that one, so we have y is equal to negative x to the power of 4, and then it's going to be plus 2x to the power of 3 minus 1000. What's the end behavior for this one? So constances do not grow, so we ignore the negative 1000 when we're analyzing end behavior, because we will definitely exceed thousands. So we have two terms to really think about. We have negative x to the power of 4, fourth degree. And then we have positive 2x to the power of 3, third degree. So fourth degree outgrows third degree in the long-term behavior. Again, you can just verify this yourself by plugging in increasingly large values. So in determining end behavior, we are only concerned with the highest degree term. There it is. What kind of degree is that? It's going to be an even degree. So it either your graph is going to go upwards for its end behavior, or it's going to go downwards for the end behavior. Always. What else do we have? We have a negative value in the front. So it's going to behave very similarly to x, like a negative parabola pointing downwards. So if you have a negative a value, it's strictly going downwards like that. Since we have fourth degree, it's going to be doing the exact same thing with a negative value in the front. So it's going to be looking something like this. Well, that's it. And behavior. Very nice. So let's do another one. So you have y is equal to x to the power of 35. And then we have minus 10,000 x to the power of 34, and then it's going to be plus 5. So, you know, let's put a few more x's. Let's do 5x to the power of 20, and then minus x to the power of 5, and then minus 40. So this is going to be our polynomial right there. Let's look at the exponents. This is the one with the highest degree. It is x power 35. This is x power 34. So this one is going to be the deciding term for how we evaluate the end behaviors. It doesn't matter that this one is one off from that one. Someone might think, wait a minute, isn't that kind of close? Like, isn't 34 kind of close to 35? So shouldn't they be kind of neck to neck in terms of their growth rates? And that's not exactly true. 35 was still, exponent 35 still outgrows 34. You can verify this by plugging in numbers. I hate plugging in for 35, but you either have to trust my word, or you can just verify it yourself. Plug in larger and larger x values, see what happens, or if you have a graphing calculator, just use that one, even better. So it doesn't even matter that there's a negative 10,000 in front of this x power 34, which again, someone might ask, like, wait a minute, this is kind of, it looks like it can keep up pace with this one, but no, it cannot, because we're plugging in, at least conceptual-wise, exceedingly large values of x. So this is definitely going to outgrow this one. Case in point, if you plug in something right past 10,000, like let's say you plug in 10,001. Is that 10,001? Yeah, this is 10,001. If you plug in 10,001, this one will be a larger size than that one. Yes. So anything after this one will outgrow in size of that one. Alright. So now that we got that out of the way, we are determining end behaviors. This is the only one we really care about when we're evaluating end behaviors. So here we go. It's going to be a positive a in the front. It's 35, so that's an odd exponent. So you have this upwards downward situation. It might be doing something goofy like this. How do you determine this one? That's coming up for factorization. Alright, so that's the most important thing is you get this upwards thing and you get this downwards thing. Because, again, as the x values get larger, what happens when you plug in a large size positive number and you raise it to 35? Well, you're going to get a large size positive y value. And then the reverse is true for plugging in large sized negative values. So if you plug in a negative 1 billion, for example, your y value also approaches a large size negative value, accounting for this downwards trend right there. Okay, so that's that. So now we'll cover the application of factorization for our polynomials. So why are you factoring stuff? Like why all this tedious exercise in getting a polynomial and then using your algorithm to factorize it. So, for example, if you have something like x squared minus 3x minus 40, for example. So why are we spending so much time learning about factorization for this one? Well, before we answer that, let's just factorize this. Factors of 4, this is a fairly straightforward. It's going to be one coefficient in the front, so that's pretty nice. So therefore, factors of 40 that add up to be negative 3. It's fairly simple. It's going to be 5 and 8. Because 5 times 8 is 40. And then 5 plus 8 could hypothetically get you a negative 3, provided you put in the correct signs, like so. So that's factorizing the quadratic. We've already gone over that multiple times, so that's speed run. Alright, so that's the factorization, and then in some classes you set it equal to 0, which, you know, depending on how your teacher explained it, it may feel like you're just doing it randomly, or you might already know the purpose of why we do this type of stuff. But let's not set it to 0 quite yet. So we started off with the polynomial in regular form, and then we factorize it to fully factored form, and the reason why we want to do that is so that we can find the zeros. And recall that zeros are almost synonymous with x-intercepts. Almost synonymous. So if you're given zeros, you can transform those into x-intercepts. And then if you're given x-intercepts, you can easily plot points. So what does that mean in regards to this current situation? So this is our parabola. We can graph our parabola somewhat using this thing right here. So here's how we do it. So if you find the 0 for this particular part, what's the 0 for this one? Well, it's whatever x value will produce 0. So we manually set x plus 5 is equal to 0. Solving for x is equal to negative 5. So what does that mean? It means that negative 5 is a 0 of your function. Meaning, if you plug in this negative 5 there, then negative 5 plus 5 gives you 0. And then 0 times anything will get you 0. Any discrete number, if you multiply 0 times a discrete value, it's going to give you 0. So that's what it means to be a 0. But going a little farther, because it's a 0, then it's also an x-intercept at that x value, which means if we plug in negative 5 right here, we're going to get 0 for our function in terms of the graph. So this particular 0, we can visually put it on our graph directly right here. Again, this point here has two values. The first value is the x-coordinate, which is negative 5, and the second coordinate is 0. So when you manually set your function equal to 0, you are deliberately finding this one in most cases. Hence the significance of finding zeros. You find zeros, you can find the x-intercepts. Finding x-intercepts allows you to plot points for your function. But that's not the only 0 that we can possibly generate, because we have another factor. Factor number 2. Can that generate a 0? And yes, it can, if x is equal to positive 8, because positive 8 minus 8 yields 0, and then 0 times a discrete value. 8 plus 15 is 13. It doesn't matter. It's a discrete value, so 0 times something else will give us 0. So count up to 8. 8, here's where x value is equal to 8. We have the x-intercept there. It's going to be positive 8, comma, 0. So what exactly has happened? We have a function. We factored the function. We found two factors. We were able to set the value, those individual factors equal to 0. So we can find x-intercept number 1 and then x-intercept number 2. Now we are going to couple this with the idea of n behaviors. This is an even exponent degree with a positive a value in the front, so we know that the graph goes upwards and upwards, left and right. And this is now where it gets a little artsy-fartsy. All you have to do is cross your x-intercepts, because you must capture those points, because that's literally, if we plug it in, it works. That's how we got those points in the first. That's why we got those points in the first place. Again, this is where it gets kind of artsy fartsy. It's gonna do something like this. So you notice that I didn't put any hash marks for the y values. So I'm not committing myself to what this x-intercept is right there. I mean, this y-intercept is right there. So that's not important at the moment. The important thing is you get the idea of the end behaviors, and then you get the importance of the x-intercepts that we can generate from the zeros. We already have a way to graph this. If you recall, we can use it. We can graph this using vertex form or just plotting points. But obviously, plotting points is the worst strat. I mean, it's simultaneously the best and simultaneously worst strat because it's super tedious. So it's only plotting points is very strong if you have an actual calculator. That would just do it for you. But if you're like in a testing situation, like you're being tested for a grade or something like that, then you have to know how to do it. Alright, let's look at another example. We're going to stick with the quadratic first. So let's say we have y is equal to x to the power of 2 minus 4x, and then it's going to be plus 4. No, not plus 4. Let's do something that's different. 12. Not 12. Minus 12. Okay. So let's just go ahead and graph this using our review. We're going to graph this using vertex form. So I hope you still remember it. Yeah. So all you have to do is group your x terms together, slap on the old parentheticals. And then you ask yourself, what's half of negative 4? It's going to be negative 2. So that's what we're going to aim for. But let's show a little bit more work. So again, what's half of negative 4? It's negative 2. And then negative 2 squared, I'm just following the algorithm. What is negative 2 squared? It's positive 4. But putting positive 4 has changed our original situation, right? This positive 4 was not anywhere to be seen. So we can't just willy-nilly change our function by putting a plus 4 right there. So we have to compensate by getting rid of this. So we're going to compensate by putting negative 4 on the outside. Because again, if you drop the parentheticals, this one combines with this one to produce 0, which takes you back to your original function. Alright. And now that this, now that this is a perfect square scenario, we can factorize it into x minus 2 times x minus 2, which is a squared. Combining those like terms, we get negative 16, and we have our vertex form for our function. Now, there's our shortcuts, of course. If you wish to go from here to vertex form a little faster, you want same central idea. What's half of negative 4? It's negative 2. Negative 2 squared is 4, right? This one doesn't have a 4, but you can split this one into negative 4, positive 4 plus negative 16. Because again, positive 4 plus negative 16 still gets you back to negative 12 if you summate those, but we can kind of skip this work here, and then this one will factorize with this one to produce x minus 2 squared, and then you have a minus 16 directly. So you can be fancy if you wish. It's a little extra, but I just want to show you that the tool is available if you wish to use it. Or you can just use the standard algorithm. Show your full work if you want full credit. But if you're doing like a standardized test and this is multiple choice, obviously you don't need to show your entire work. It will be a waste of time. Alright, so that's the function. Let us graph this one using vertex form yet again. So the idea is you can extract the vertex. Vertex is typically at 0, 0 for your standard x squared y is equal to x squared function. Where do we drag that vertex? We're going to drag it 2 spaces to the right, so 1, 2. And then 16 spaces downwards, so somewhere down here. Obviously not to scale, unfortunately. It is what it is. Let me put this. Yeah, so let's say this is negative 16, and this is positive 2. Okay, and then because the a value in the front is just a positive 1, it's going to go 1 to 1, negative 1 to positive 1, and then positive 2 to positive 4, positive 2 to positive 4, and positive 3 to positive 9. So something funky like this. Just graphing it using vertex form. All right, so that's the old stuff, right? That's the old skill we already have. Oh, unfortunately, I'm kind of slipping on this one. Something like this. Okay, that's using our old school method of graphing via vertex form. We can now also graph using x-intercepts, but we gotta factorize this. So how do you factorize x minus 4? X squared minus 4x minus 12. Again, factors of 12 that summate to be negative 4. X minus 6, and then x plus 2. What are these zeros? Let's find the zeros. So the 0 for factor number 1 is if x is equal to positive 6. So we count up to 6. Here it is. It's supposed to be right here. So that's 6 right there if I had drawn to scale. And of course this other one, what's the 0? If x is equal to negative 2. So here it is, ish. And those are our two zeros, and then we couple that with the idea of n behaviors. What's the n behavior for this particular function? Well, it's going to be positive coefficient to the power of an even exponent. So we're going to have an upwards n behavior, and then that's it. All you have to do is connect it as smoothly as possible. How did I know it's down here? We don't. So if you're just doing this artsy-fartsy style, it'll be something like this. We would not know how high or how low to place this one unless we plug in more values. But again, I just wish to emphasize n behaviors and x-intercepts. Vertex form actually tells you where the vertex is. Wonderful. So that's with the polynomial of the type quadratics. But what if you don't have a quadratic polynomial? What if you have something else? Well, it's practically the same thing. You need to factorize, and then you need to ask yourself, what are the zeros? And once you figure out the zeros, you graph the x-intercepts, and you couple that with the n behaviors. So let me show you something that's already factorized. So suppose your polynomial, you've already factorized it into something like x plus 2 times x minus 2 times, this is just a quadratic, but this whole thing is going to be x minus 4, for example. So you already did your synthetic division, and this is what you factorized your polynomial into. So how do you graph this? You start off with your x-intercept ideas first. So this is x-intercept number 1. It's occurring at negative 2. So there's negative 2. There's your first x-intercept from left to right. Then you have your second x-intercept. That's x is equal to positive 2. So your x-intercept should occur at positive 2. Of course, you have your third one. X is equal to positive 4. It's going to be right there-ish. So we have 3 x-intercepts because we were able to find 3 zeros. Again, the zeros are intertwined with the idea of x-intercepts. So that's nice. Let me make those points more explicit. There's a point there, and there's a point there. Okay. So if your function, let's just color it red, what's the n behavior? Well, unfortunately, this is fully factored form. So we have to go a little bit backwards by distributing. So here's how you determine your greatest degree exponent. All you have to do is multiply your greatest degree x's within your factors. So x times x times x gives you x cubed. Make note of the signage. This is positive x power 1. This is positive x power 1, and this is positive 1 x power 1. So that is going to be your leading term with the highest degree possible, which is just 3. What does that mean? It means that we have an odd powered exponent, and then with a positive a coefficient, so it's going to be doing the down-up situation, like so. Because again, if you cube a large size negative value and you apply this thing to it, it's still going to be a large size negative value. So it's going to be, as x approaches negative infinity, y approaches also negative infinity, accounting for this one. And of course, if you look at the other end behavior, as x approaches a large sized positive value, then the y value also approaches a large sized positive value. Right there. So we have the 3 x-intercepts, we have the arrows. So all you need to do is try to connect them as smoothly as possible. So here's how you do this one. This one will have to intercept this one right here. It has to. And then it'll be going upwards somehow. Eventually it will swing back down. Don't worry about where it's swinging back down, but somewhere along the way it's going to swing back down, and then it's going to cross this one, intercept ring right here. Going downwards, and eventually it will turn around somewhere. Again, don't worry about where this is occurring. You can use calculus for that later. It's going to be swinging back upwards, crossing this x-intercept because it has to, because that's literally what we found. And then it has to be going backwards up, connecting to this end behavior. And then you are done graphing this polynomial function. Very nice. Just a few things to make note. How come you know that your graph isn't doing something else? How do you know that your graph isn't doing something funky like this? How do you know this? Well, number one, the end behaviors are in disagreement. So let's redraw that one. How do you know your graph isn't doing something funky like this? Because if you draw it like this, you are implying that there's another 0 here and another 0 there, which, where are they? We have a 0 at -2, that's this one. We have a 0 at +2, that's that one. And then we have a 0 at 4, which is that one. Where did these ones come from? They came from nowhere. So that's, you know, your graph doesn't cross the x-axis anywhere else other than these 3 points. So there's no shenanigans that you don't get these random things right here. You know for certain that you will never cross anywhere else. So there's no crossing the x-axis here, no crossing the x-axis there, nor there, nor there. These are your only instances where your graph, your function, where the graph of your function will cross the x-axis. It's only these points. You won't have anything else. So we know it has to be, and we have to cross through it. We have to cross because that point is included. Because if x value is -2, then y value has to be 0. So you must include that point. And again, they're the only instances where you cross your x-axis. So that's the significance of the x-intercepts. So again, artsy-fartsy, where does it turn back down? Who cares at the moment? It's going to turn eventually somewhere, and then it crosses back here. Turns around somewhere, crosses back up to join with the end behavior right there. Right there. And that's finished with this particular problem. But let's go back just a little bit because I do want to talk about where this thing came from. Because this one, it will already be distributed for you typically. Sometimes not. So how do I know this is the greatest degree possible? Well, you kind of reason it out by looking at the factors. So if we take this factor number 1 and we distribute it to factor number 2, you think about what's the greatest possible degree you can get from there. Well, this one doesn't have an x, so if you distribute this thing to that one, you're not going to have you're going to have x power 1. If you distribute this 2 to this x power 1, you get exponent degree 1. So that's why we don't pay attention to this 2, because it doesn't have an x. Well, it does have an x, but the x is exponent 0, so we pay attention to the larger degree of these two first, which is just this one. So if you distribute this one to this one, it will distribute to, what do we care about? Just the one with the greatest x degree. So it's just this one, because this one doesn't have an x degree. So maximizing the degrees possible, the greatest degree possible by distributing this one to that factor is only x power 2. Keeping track of the coefficients, it's going to be 1 times 1. So from the product of those two factors, the greatest degree possible is this one. So if you distribute this one to the third factor, again, you look for the largest degree possible. It's x power 1. So if you distribute x power 2 to x power 1, you add the exponent, and you get x cubed. And that's it. Like I said, it's usually you look over the examples and it'll make a lot more sense. So let us do something that's already, again, fully factored form. So let us look at something like 2 minus 3x times x plus 5, and then times x minus 3. Let's do one more. Let's do x minus 10. Alright. So, looking at the situation, we have this many factors. We have factor number 1, factor number 2, number 3, and number 4. So we should have 4 x-intercepts right off the bat. So let me color code them. This is going to be the blue one. This is going to be green one. This is going to be magenta. And then this will be orange. So what are we supposed to do in terms of the graphing? All you have to do is plot the zeros, the x-intercepts. So the zeros, what's the 0 for this one? The 0 is negative... No, I'm sorry, positive 2/3. Again, if you plug it in, 2/3 times negative 3 is negative 2. Negative 2 plus 2 is 0. So this whole thing becomes 0. 2/3 is right here. I'm just kind of eyeballing it for the placement. Alright, and then of course you have a 0 for this one. What's the 0? That one's a lot easier to see. It's negative 5 plus 5 is 0. So let's pretend here is negative 5. So this is going to be x-intercept green. X-intercept blue right there. And of course for the magenta, how do you make 0? If x is equal to positive 3. So this is x-intercept number 3, magenta. And then lastly, how do we make this into 0? If x is equal to positive 10, and that's going to be our third x-intercept. I mean our fourth x-intercept, I'm sorry. So that's at positive 10, and then magenta is again at positive 3. So next task is to determine the end behavior of our function, and like I said, all you need to do is pay attention. You need to just do partial distribution. Don't sit there and distribute this whole thing, because that's really annoying. Because if you distribute this one to this one, you're going to get 4 terms right off the bat. You can combine it and make 3 terms, and then this one distributes to be 3 terms. So you have to do 3 terms times 3 terms, which you will immediately end up with 9 terms, but you could collapse and make like, what was it? Something like 5 terms, I think. So it's a lot of work. It's really tedious. You don't need to do it. All you need to do is consider what's the highest possible degree term you can get. So you only pay attention to the x with the highest degrees, and you distribute those ones to other greatest x degrees for each factor. This is only for end behaviors. So for this first factor, the greatest degree possible, this one is x with a degree 0, this is x with a degree 1, so we're going to be taking this one first. So that's the greatest degree possible from the first term. We have to keep the coefficient in the front, because that's literally what it is. This one will follow through as you distribute. So you pay attention to factor number 2, which of those two has the greater degree. It's just this one. We will have to multiply this one times this one somewhere along the way. So this is the highest possible degree you can get from distributing those two. So once we're done with that one and we distribute to the third factor, what's the greatest possible degree achievable? Which of those two has a greater degree? Just this x. So we will have to distribute to just that x somewhere along the way. So that's done with the third factor distribution, and then after we distributed those 3 factors, this one will eventually get distributed to this one. The most relevant one is just this exponent 1, not this constant minus 10. So when we distribute somewhere along the way, this will have to distribute to this one. And that will get you the greatest degree possible. So what is this times this times this times this? Following your exponential rule, it's going to be negative 3x to the power of 4. So that one will be your leading term. It's a lot faster. I'm just talking through the steps. So when you're on your own and you're doing these type of problems, you can just pick the largest terms and distribute them for a partial distribution, and that will get you the leading term. All right, so the leading term is negative 3x to the power of 4. It is a negative a value. It is an even, what's that word? It's an even exponent, so it's going to be doing parabola upwards behavior, but it's reflected downwards, so you have a downwards type of end behavior. So move on to your graph. Let's get to graphing your entire function. So again, what's happening? It's like parabola-like, but both end behaviors are going downwards. So we can say that as x approaches negative infinity, then y also approaches negative infinity. End behavior number 1, like so. And then end behavior number 2, as x approaches positive infinity, y also, as before, approaches negative infinity. So downwards behavior. So understand that idea. I'm going to make a quick comment in terms of the artsiness of the situation. Some people put the arrows like way off on the side like this one, and then they do something goofy like this. It looks really weird. Especially for higher degree polynomials, you just want to put your arrow very close to the first x-intercept. Like if you imagine drawing a line straight through, perpendicular to the x-axis, your arrow is going to go very close to that line. So I tend to put my arrow like right here, because when you connect those two as smoothly as possible, it looks nice. But in contrast, if you put it goofily off to the side, you're going to be doing something weird like this. And that, to me, it looks really bad. So don't do that. It's not a big deal, honestly, but again, that's just my personal preference. I prefer to put it very close to this one, like so. Downwards. So all you have to do is connect those as smoothly as possible. Make sure you cross all your x-intercepts. So that's intercept number 1. Where does it turn? We don't care at the moment. Crossing that one. Where does it turn? We don't care at the moment. Just swing it back up somewhere along the way. Crosses through the x-axis, and then swing it back down just to agree with the end behaviors. So you have to have the end behaviors agree. You have to intersect all those x-intercepts. That's why they're called x-intercepts. You must intercept at those locations. How do we find those? By finding the zeros. How do we find the end behaviors? By doing partial distribution of the greatest degrees per factor. Alright. Let's do another one, of course. Let's do a goofy one. No, let's do a normal one, and then we'll do a goofy one. So y is equal to, we're going to have negative 3x in the front, and this is going to be x minus 5. X plus 5, actually. And then we have 3 minus x. And then we have 10 minus x. So what do we have? Take a quick survey. We have some sort of polynomial. We have factor number 1. Well, technically this is one factor, but I'll count this as one factor. So we have factor number 1, factor number 2, factor number 3, and factor number 4 yet again. So we have 4 factors like the previous situation. This is one factor. We can get the 0 if x is equal to 0. So that's the 0 of factor number 1. What's the 0 of factor number 2? Negative 5. What's the 0 for factor number 3? X is equal to positive 3. What is the factor for what is the 0 for factor number 4? It's positive 10. So we have 4 distinct zeros, which means we have 4 distinct x-intercepts. So let us get to the graphing by plotting those 4 points first. So the first 0, in no particular order, is right there. Second 0 is at negative 5. And third 0 is going to be at positive 3. And lastly, fourth 0 is going to be at positive 10. Here-ish. So what's the end behavior of this particular function? Well, that's going to be fun. Well, you go through each, you comb through each factor and you take the greatest degree. Well, this one only has x, only one thing to consider, but make sure you keep that negative 3 attached to this one. So the greatest possible x term we can get from first term is literally itself, is the negative 3x. What's the greatest term x degree we can get from here? It's just x power 1. What's the greatest degree x term we can get from this third factor? It's negative x. Fourth factor, it's also negative x. So you notice again, I've kept the sign, the coefficients attached. This is coefficient 1. This is coefficient negative 3. You have to keep those because when you distribute those x terms, they distribute with their coefficients. So combining all this together, we have a negative sign still, and then we have 3, and then we have 1, 2, 3, 4. So that is going to be our leading term. Like the previous problem, we have a negative value. It is an even powered exponent, so it's going to be downwards, downwards for the end behavior. So let's get to graphing this. Again, I like putting the arrow very close to this one. It's going downwards. Still too close. I'll put it like right here. Downwards. This one is downwards. So we have our end behaviors. We have our 4 x-intercepts. We just need to graph this as smoothly as possible. You have to turn around sometime. And here's my personal preference. I don't turn them around. I just put it arbitrarily. I just cut it off. It just goes off screen. And then it goes back downwards. Because I don't want to commit to where it turns. So I'm going to be a coward and just cut it off like so. And then this one goes downward. It'll turn around somewhere, but again, I'm going to cut it off visually. Goes upwards, but you notice I do it tilted enough so you know where it's going. Something like this. It's going to turn around eventually, but I'm going to omit it by cutting it off. And that's it for the graph of the function. So if you imagine this is on your graphing viewing window, it looks something like this. And that's how I personally do it. Again, you can just put willy-nilly. You can put this hump anywhere you wish. Obviously, if you want a higher degree of visual accuracy, you just plug in a point arbitrarily between those two and it'll give you close to the hump, typically halfway. So if you find halfways between this one, it's like roughly like maybe 6 or 7, depending on what you want to do. You plug it in to your function and you get your corresponding y value, but it's a real pain. It's not worth it in my opinion. So I just cheat and just cut it off screen. Very simple. And we're done graphing this particular situation. Let's get to the funky situations. So if you have y is equal to x times x minus 5 times x minus 5. So this is a repeated, this factor here is the same as this factor there, so we can combine them, simply summating the exponents. So y minus 5 quantity squared. So how do we graph this thing right here? Well, you ask yourself, how many zeros do I got? We have 0 number 1, that's the easy one. Literally just x is equal to 0. And then you have 0 number 2. X is equal to positive 5. And just as a quick note, this is technically 2 zeros right here. The word for to describe the situation is this is a factor of multiplicity 2. This is a factor of multiplicity 1. Which will come into play a little bit, but for now, just understand that we have 2 zeros here. We technically have 2 zeros, but they are repeated zeros. Because again, if I had left this in expanded form, let's say I didn't put this exponent, and I left it like this one, this is also a 0. But it's just repeated. So we don't explicitly write it out like that. But technically, 2 zeros right there, which becomes important. Trust me. So let's get to graphing. How do we graph this situation? So when people are starting off, they see, oh, x is equal to 0. That's easy. And then they see x is equal to 5. That's also easy. So let's determine the end behaviors for this one. We have exponent 1. We have exponent 1 from the first factor. Remember, there's technically a second factor. If you ignore this 2 and you expand it out, we have a third one right here. Or you could just do partial distribution here as well. So if you partially distribute this exponent to this one, the greatest degree possible is exponent 2. So when you simplify this junk, keeping track of all the coefficients, of course, you're going to get x power 3. And that is your leading term. So it's going to be doing the down-up end behavior situation. So for this one, it's going to be going downwards, and then for this one, you have it going upwards afterwards. And this is where things could potentially go wrong when people first start graphing these things. They might be doing something like this. They're like, okay, and then wait a minute, like what? Like how do I'm clearly going down, how do I go back up to right here? So they might do something like this, which, you know, that's a problem, of course, for two reasons. One reason, it looks really ugly, and another, more correct reason, this implies that by doing a graph like this, the implication is that there is a third unique factor right there, a third unique 0. But we only have 2 unique zeros. We don't have 3 unique zeros, so this is definitely wrong. So we have to backtrack just a little bit, and we have to understand that there is a repeated solution right here because it has 2 of them, right? So if you were to extract this in your brain, just take this one right here and extract it in your brain, you have x minus 5 to the power of 2. Isn't that just a parabola? If you think about this, if you graph this one, it's just going to be looking something like this, right? And you know what? That's exactly what happens. Because this parabola entity, this parabola-like factor exists right here, it actually behaves parabolic at that particular 0. It's going to be doing this parabola-looking, mini parabola-looking thing right here. And that's this portion right there. So all you need to do is make sure this one agrees with the rest of the visuals of your function, the graph of your function. So this is actually, I'm going to move this over just a little bit, because at this particular 0, it's going to be doing a parabola-like behavior because it's parabola-like with an even exponent right there. So again, this part is that part, a mini parabola because even exponent. Alright, and all you need to do is connect this one to this one as smoothly as possible. So I'm going to cheat just a little bit. Perks of the digital medium. And as for this one, it's just one unique factor, so we're going to have to pass through it. So that one's pretty okay. So all we need to do is connect these portions to our end behaviors, and we will have successfully generated the graph of our function. So connect it as smoothly as possible. I'm going to go off screen again. I'm going back on screen. You can choose to put the hump there if you wish. I'm going to ignore it. Just make sure you connect this one to that one as smoothly as possible, and then we have successfully generated the graph of our function. Here's the viewing window again. So it could be, again, doing something like this. Alright. And that's basically it. So again, the fact that we have this little touch and go situation is because we have this parabolic-like nature right there. So this is the correct graph. Let me show you the incorrect graph. A potential pitfall that someone might do. So here is a mistake that I've seen before. So someone can do something like this. They're like, oh, there are 2 points. If I just try to pierce right through them, it's not going to work out because I get this third random 0 that should not exist. So what they can do instead sometimes is they do the touch and go at the wrong location. They wrap it back around and they get something like this, and this is going to be a wrong situation. This is the wrong graph because what this one is saying, the visual here is saying we have the touch and go at the 0, but we don't have that because this is x power odd, x power 1 odd power. So this one's definitely not parabola-like, so why are we putting the parabola motif at this particular 0? It should be the parabolic like motif is supposed to be happening at the parabola like exponent 2. Even powered exponent gives you the touch and go. Odd powered exponent gives you the straight pierce through. Okay, so another example just to drive that point home. So suppose we have something like y is equal to, let's do x minus 3, x plus 3 cubed. You notice now I'm using an odd degree that's greater than 1. And then times x minus 2, x power 4. Let me do 2 first. And then we have a third one, a unique third one, x minus 5 power 4. So let's say that's going to be our polynomial function. Let's get to putting the graph x-axis here, y-axis there. Okay, so again, already given in fully factored form, we have a 0 right here. What's the 0? It's of x is equal to negative 3. It's of multiplicity 3. So keep track of that idea, okay? So this 0 is technically repeated 3 times, but it's not unique. So there are 3 non-unique zeros at this location for that x value. And then for the next one right here, what's the 0? X is equal to positive 2. It's multiplicity 2, which means we have this same solution repeated twice. And then for the third one, the third unique factor, we have x is equal to positive 5 as a 0 of multiplicity 4. So the 0 is repeated 4 times. Keep track of that. Alright, and then lastly, we need to determine the highest degree. We can do partial distribution for that one, just to get it. So if you distribute this exponent, the greatest degree you can get is x power 3 from there. We're ignoring all the other terms because they will not have x degree 3. So visually, if you want to see the visual, it's just going to be x plus 3 times x plus 3 times x plus 3. So when I do this partial distribution of 3 exponent to this one, I'm just doing this one times this one times that one, because I don't care about the other terms. They're not going to produce a high enough degree. So the highest possible degree we can get from this one is solely x cubed. And then of course for this one, by using partial distribution, is x power 2, partial distribution, x power 4. Again, I've kept track of the coefficients as well. They just happen to be 1. So what's this one times this one times this one? We're going to get the leading term is going to be positive x power 2 plus 4 is 6, plus 3 is 9. So that is our leading term. We have an odd exponent, and then we have a positive a value in the front. So we know for sure it's going to be doing a down-up behavior as specified before. Okay, so let's start planting the x-intercepts. So we have x-intercept as negative 3. I'm just going to eyeball it like here-ish. It is of odd degree, so we know that it's going to do a strike through. So it doesn't do the parabola thing because this is an odd powered exponent. If it's odd, it just pierces right through. Like so. Okay? Again, the reason why is because on one side, if you have a negative value and you cube it, it's still negative. But on the quote-unquote other side, if you have a positive value, if you have like negative 2.5 for instance, and then you add it to 3 and then you cube it, you end up with a positive value, which is why you cross over. Okay, but if you don't want to think about that, if it's odd power, it's like linear function, you just pierce right through. If it's even powered, then it does a parabola like motif. So even powered at x is equal to 2, it goes upwards because this is positive with a squared. Yeah, so upwards. Again, parabola motif right there. And then for the final x-intercept, what's happening there? We have even powered exponent on the x. Oh, I didn't even graph this part, I'm sorry. Let's graph it right here. Let's pause at 5. What's happening there? Also a parabola-like behavior because this is even powered exponent at this particular x-intercept right there. So we also have an upwards motif, not downwards. How can we know it's not downwards? Well, it's because this whole thing, this leading part, is positive. Maybe we'll talk about this in a later example, what happens right here. But it's going to be going upwards. Alright, and then now we just need to merge those ideas with our visuals for the end behaviors. So let me just move this slightly right here-ish, and then we move this one to accommodate this particular motion. Here's my eyeball right here. And now let's just connect these as smoothly as possible to generate our function graph. Like this, it goes upwards. Again, I'm going to make it go off screen, and then comes loops back around at some point, hits this one, does the touch and go, because again, this is an even powered parabola-like motif. Goes back upwards. It's going to loop back around somewhere. Going back here. The touch and go again, because this is even powered exponent. It's going to do a parabola-like motif. Go back up. I'm going to just put the viewing window just to show that I've cut off parts of the graph. And that's it. That's how you graph this particular example. Again, just find the x-intercepts, the unique x-intercepts. Fuss over the multiplicity at those ones. Again, if it's even powered exponent, you do the touch and go. If it's an odd powered exponent, you do the pierce through. Alright, and just a few more things to go over. Let me just go back just a little bit. There are some nuances to pay attention to. So for this particular zero, right, how do I know that it's like this rather than something like that? Okay, there are two main reasons. Again, the main reason, number one, we already mentioned it. So this is where the zero is occurring. So if you have an x value that is that's like a larger size negative, like 3.5, and you plug that one in, you're going to get a negative value in here. And if you cube it, it's still negative. So that's why you're down here. But when you plug in an x value that is past negative 3, like x is equal to negative 2.5, for example, if you plug that in, it becomes positive. And if you cube a positive, it's still positive. So you end up above here. So that's why we know that it's tilted like this. So that's if you think about plugging and chugging. But if you're particularly lazy, like I am, what you can do is, all you need to do is, if you already determine the end behavior, then this one, which is the first zero from left to right, because it's the only negative zero. That sounds weird, the only negative zero. It's the only negative x value that gets you a 0, then this one has to connect to this end behavior. So you know that it's going to tilt over to here. It's not going to tilt over like that, you know what I mean? So two main reasons. Okay, so that's why you should put the end behaviors first. I guess the ordering doesn't matter, but just make sure you think about, make sure there's proper synergy between the end behaviors and then the x-intercepts. So again, this one right here, we know it's going to be going tilted like this because it must attach to this one. And then how do we know that this one, the 0 here, goes upwards? Like, how do we know it's like that? How do we know it's, how come it's not like this one? And when does this one happen? Well, strongest reason, number one, is because in order to continue the smoothness of this function, we have to eventually turn back down to hit this one right there. We know it doesn't pierce right through because it's the parabola-like nature of it. So it has to, we have to go up from this first x-intercept. We have to go back down. We have to hit the x-intercept at 2, but we do the bounce back up because it's parabola-like. So you cannot achieve that if you hypothesize it like this. So if you manually start like this one, there's no way to connect this one to this one continuously. Like, you have to cross somewhere. This introduces a new x-intercept. This x-intercept isn't supposed to be there. So that's how we know this is not down, down. Or, like before, you could, in your mind's eye, plug in values that are close to around 2. So if you plug in positive 1 and positive 3, for example, if you plug in positive 1, it doesn't matter if it's plus or minus, because if you square it, it's positive. So if you plug in 3, for example, 3 minus 2, it doesn't matter if it's plus or minus. It gets squared, it's still positive. So that's why we know it's like this. Alright. I guess that might be a little tricky, right? Let me think about that for a moment. Because if you have a negative value arbitrarily, then the leading term will be negative x power 9. Which will essentially just flip those two end behaviors. So that will be going downwards, downwards. Okay, so you have to take into account signages as well. So it's easier to determine for this one. No, you know what? I'm going to backtrack this a little bit. I'm going to backpedal. Plant the correct end behavior arrows first, and that will always guide you into determining whether or not you make it go downwards, downwards, or upwards, upwards. I'm going to maintain that answer. Okay. So let's do one more for the road for the tutorial. So if we have y is equal to 2, let's do with a negative sign in the front. Let's do x plus 3 power 5 times, let me move this over just a little bit. So negative 3x, for example. Let's say we have that one, and then we have here x minus. No, I want it to be farther out. X minus 4, let's say that this is powered to 11. And then we have times x minus 6. This is exponent 20. These huge numbers aren't going to matter. You just need to think about whether or not it's a plus or minus is important. Wait, what am I saying? If it's just think about, it doesn't matter how large these ones, just think about whether or not it's even or odd. There you go. So this is going to be the pierce through in terms of the graph. This is going to be pierce through in terms of the graph, and this is going to be the touch and go because it's parabola-like, because even powered exponents. This is technically x power 1, so that's just pierce through. Let me change this and put it exponent 4. So now that it's exponent 4, we have the touch and go at this particular 0. Okay, so now let's do the leading term first. So we have term number 1. It's going to be the negative 3x power 4. Remember, keep the coefficient associated with the highest degree. And from the second unique factor, multiplicity 5, we can get the greatest term is x power 1. And then from the third factor, multiplicity 11, the greatest x term is x. Oh, I'm sorry, backtrack. This is partial distribution, so this is exponent 5. There you go. Because if you sit there and multiply it out, you will have at one point x times x times x times x times x, because it's exponent 5, leading to this one. And then for the third one, we have highest degree is x, partial distribution, just to get the idea, exponent 11. This one, partial distribution, exponent 20. So when you sit there and crunch the numbers, we have first the coefficient, which is just negative 3, and then you add up all the exponents. This is 9, 20, 40. Whoops, x power 40. So what does it mean for our end behavior? Negative a value, this is even degree. So it's either be going in, it's like a parabola like in nature, but since we have a negative in front, that means it's going downwards, downwards for the end behavior. So downwards and downwards. So now let's find the zeros. We have a 0 here. That's 0. It's multiplicity 4. I'm not going to, we know it's going to be parabolic, so it's either going to be upwards, upwards like that, or downwards, downwards. But let's find the leftmost 0 first. So is it this one? Maybe not. What's this one? Coloring magenta. This is at x value negative 3, so that one's the farthest left so far. there's that one, and then we have the green one right here. That is x is equal to positive 4. So here-ish. Then we have 0 at x positive 6. So somewhere right here-ish. So the leftmost 0 is magenta. So I'm going to, now we can determine the motifs, the local motifs happening around those zeros. For this one, it's going to be odd powered exponent. So we know it's going to be a pierce through. The end behavior is going downwards. So let me move this over. So we know it's going to be tilted like this, not tilted like that, because we must contact this end behavior. So like this. What's happening at the blue one? Well, it's multiplicity 4, so that's even, so that's parabolic at that particular 0. We know it has to connect it to this one somehow, so it has to be upwards. And then green 0, we have 0 right there. It is odd multiplicity, so we know it has to connect to this one somewhere along the way, so it has to be tilted like this one. Lastly, we have a 0 at the orange. It is of even exponent, so it's parabola-like. It has to be downwards in order to connect with this end behavior. So it has to downwards like this. It cannot be upwards. Otherwise, how can you connect this to the end behavior we already predetermined? So it must be going like this. So at this point, you just need to beautify your graph. I'm going to move this end behavior a little more to the right just to make it nicer looking. Squish it just a little bit. Oh, right here. Okay, and now we connect as smoothly as possible. So here to here. And then you can do the loop-de-loop like this, but again, I just prefer to go off screen because I don't want to commit to an actual turning point without calculus. And then right here is going to go upwards, tilted slightly. This one right here. So again, there's technically a turnaround somewhere and turnaround somewhere. Right here, same thing. Goes downwards. There's some sort of turnaround somewhere. Back up. Connect those as smoothly as possible. And this is going to be the viewing window that I'm trying to emphasize. And we are done with this particular situation. Okay. I think Rumi's back. And food has been obtained. So I'm going to call it here. I'll probably be back some other time later. There's going to be... This is just a tutorial. So I'm going to be going through the full motions of synthetic division factoring to generate the fully factored form and then graphing from there. So that'll be it for now. You have a good one. I'll see you in the next time.